So let's do the energy. As I said, storing energy either in a charge or can be thought of as being associated with the charge or associated with the field in between the plates. It's pretty easy to work out, actually. Energy is, remember, we said that the battery is doing work by pushing the charge around or create essentially. My model that I like is the whole idea of the potential hill. You remember I took a board and I said that before you put the battery in the circuit, before you flip the switch, the charge sees something that could be related to a flat surface if you relate it to a mass in a gravitational field. And when you flip the switch, the battery does work on the entire circuit and creates something that analogously could be considered a potential hill, so that there's a lower potential, electric potential, i.e. voltage, at the bottom and a high potential at the top, and the charge flows down that hill. And when it's at the bottom, the battery also acts like a motor, takes the charge and puts it back on top of the hill, keeps doing that. And ironically, for charge, there's really two hills. There's one for the positive charge, the holes, and there's one for the negative charge that are actually the only thing that's moving, that flow down. But it's all the same, basically, they add to one another. But really, in effect, there's ultimately only one charge, and we talk about why there's, the total charge of the capacitor is not 2Q or 0, but Q, all that stuff. So remember all of that we talked about at the beginning of introducing capacitors. So, the battery then is work per unit charge, pushing the charge around, or you can think of it as creating the potential hill in the first place that allowed the charge to flow down that hill. And so at any rate, the energy that's stored in the capacitor is coming from work done by the battery, however you want to think about it. So we can remind you about a little circuit here. So capacitor is continued. And this is stored energy. So essentially, electrical potential energy also. That's how we can think about it. Remember, this thing should have some sort of resistance in it, but we're not really focusing on that right now. So we're not drawing the symbol that would represent the resistance. But it would have to be there in order to charge the flow in the first place, as we will find out next chapter. So let me go ahead and switch here. Positive, negative, delta V, C. And so, sure, when I flip that switch, all the stuff that we talked about previously will happen. Flip the switch, charge will flow around, and they'll begin to charge up the capacitor. So we're going to have maybe I should put it on the inside, but whatever. Here we go. Sensible analogy. And then you have the field. So there's the plus Q, minus Q. And the important thing also is that there's a potential difference. So the capacitance, of course, there's a capacitance associated with the circuit. And when the capacitor is fully charged, there's a delta V from one part of the circuit to the other part of the circuit that's there. That delta V will be equal to the potential of the battery. That's, as you move across, but that potential will be opposite in polarity relative to the circuit as we talked about, right? Plus, Q minus. So in order to determine the energy in the thing, we do it just like we did with mechanics. How did we do that? We used a work function. We said that in general, work is equal to the integral of F dot dx. Actually, you know what? We can go a different. I could do it that way, but let's go a different route. This is more straightforward. So I was going to get that in. But let's start with the definition of capacitance. We said that capacitance was defined as the change in potential energy over the charge, right? So a particular charge. Now, we could make that the total charge, but it's just some for a particular charge. Right? So that's like the charge of each, the work done to put each individual charge. But if I want to get the total work done, right? Total work, and also remember that by the general definition of potential energy, work is equal to the negative of the change in potential energy. So let's keep these concepts in mind. Remember, we're teaching concepts, not equations. So this is the definition of capacitance. It's this equation. This equation is the general definition of potential energy for mechanics. General def of potential energy. Now we can take the absolute value and do that. Then I can just say, I'll go ahead and do that now. The potential energy of the work is equal to delta U. And also, like the charge that's actually on the capacitor plates is cumulative. So I like to put this in just to remind myself that if I want to get the total work done of the battery charging up the capacitor to its fullest, then this equation really is, I can substitute 3 into 2, 3 into 1, and also remember that I'm dealing with a net charge on the capacitor. So you might think of it something like this. The total work is gonna, we can figure out the total work to put the total charge Q on the thing. And let's make this symbol back to capital Q here. So Q plus, Q negative. So what I'm trying to say is Q is equal to the net of all the little Q sub i's, where the Q sub i's are the individual charges being placed on the capacitor. And remember, even though I have plus Q and minus Q, the total charge, right, on the capacitor is just Q, because the actual thing is on the electron. So remember that Q plus equals Q negative, and the total charge is just Q. So that's this Q here. So everybody got that? Everybody got that? Now, actually, I had a delta here, so let me keep that. This, yeah, we'll go with the, if we assume that delta represents the amount of work and the energy associated with an individual charge, then I can keep a delta in here, I guess. And technically, I don't know. Yeah, I guess we can do that. And I guess it should keep a DQ as well. We can look at, because this summation implies kind of, you know, we can do this mathematically. We know that there are actual individual charges being placed on there, but theoretically, we could kind of think of it as a differential charge. We know that it's, you know, mathematically speaking, we could just take a smallest amount of charge, even though I know it's not physical, but, you know, a differential element of charge can be even smaller than the actual charge that's moving around. We can just do it from a theoretical mathematical point of view, I guess. So you might not see something like this in the book, but it's just kind of my way of thinking about what's actually happening. But ultimately, I'm going to take this in the limit as this thing gets, the individual charge gets really small. I can think of it as a DQ, that I'm really a DQ associated with the DW. So there's a differential amount of work done by the smallest differential amount of charge that's placed on the capacitor plate. And so then we can convert, you know, in the limit as delta Q gets really, really small, this equation becomes, equation 4 becomes that the capacitance is equal to the differential amount of work over a differential amount of charge. And so therefore the total amount of work done, we could integrate that. So we could solve this for work until we have C dQ, right? And so when we integrate both sides, we're going to get that the total work is going to be equal to the integral of the charge. Now, the capacitance in general is constant, so it comes out of the integration. And we get that the total work done, the charge of the capacitor is equal to the capacitance comes out. Is that right? That's right. Oh, wait a minute, what's happening here, dude? What's happening here? Oh, yeah, right. Oh, what am I doing here? I'm so sorry, folks. I'm screwing y'all up so bad. This is Monday morning. I don't know what did I have? This is not capacitance.
Yeah, this is not the formula for that, Professor.
This is potential. Yeah. What? Sorry. I'm writing capacitance and thinking potential. Yeah, I'm so sorry. That's potential. So delta V. My bad. Yeah, it's, oh gosh, sorry, delta V. And delta V. That still doesn't change anything theoretically, right? What I'm trying to say, like everything that was I mean, I didn't really say much about capacity. I was really talking about the right side of the equation, and I just had it equal to the wrong thing. Right? Because clearly the capacitance wouldn't be constant if that were the case, and it is constant. Right? That's a different formula. So it's potential. I'm so sorry. Wow. Potential. Right. So the work is equal to the change in potential times the PQ. You can define the initial potential as 0, Okay, you can do that. And yeah, wow. So sorry, that's crazy. Just making this more complicated than it needs to be. So everything is basically true. It's just that every place I had a C up till now, place a delta V. Now remember that delta V, thank you for whoever said that. Delta V is equal to like V final minus V initial. But you know, you can say that the initial potential of the capacitor is 0 before you charge the thing up. So you can define initial potential as 0. So we're just dealing with the final potential after it's charged, right? So that becomes work is equal to, basically put 8 and 9 into this guy. And the work will be equal to integral of V dq. Okay, everybody with me? Hope I didn't throw you off like that. Everybody with me? Maybe I got this resistance. I got a bunch of noise in here. Can you not hear me? Is it still messed up? I got the air conditioner on.
It's good. A little chirping in the background, but it's okay.
Is that better?
No? Yep, it's quiet now.
All right, cool. So yes, just want to make sure before I finish this up, everybody good? What I'm doing here? No questions. Gita, how you doing this morning? Doing all right? You there, Gita? Thank you, Brian, for the thumbs up. Hey, CL. Oh yeah, good. So hey, CL, is there any update on? Weren't you having some issues with Wiley? Any update on that? Did they get back and did they contact you? Maybe he's not there. Morning, Julia. How you doing? Ron and y'all, the regulars. Yes, I was able to. Oh, wonderful. Good. Awesome. So if you need any help with if you got behind on the homework, I can give you some extension. I think there's some dates that haven't come up yet, but let me know and I can extend the time for you if you need that on the homework. So go ahead and work on. I think there's 3 homework sets that I assigned. Wonderful. Good job. All right, so let's knock this out then. So now we're straight. And now we can put in the thing for capacity equation. So this is not the definition of capacitance. This is the definition of potential. Sorry, potential. Potential is, you know, voltage is energy per unit charge. So this is the definition of electric potential. Brain fart. Sorry. So definition of electric potential, definition of general definition of potential energy. And now we can do the definition of capacitance. Remember, capacitance is defined as charge per unit volume, per voltage, delta V. Now, definition of capacitance. That's what I get for doing this without looking at my notes. Little mistakes like that. And so from 10, we can solve this for delta V. Delta V becomes, well, we said, sorry, V, we've taken that to, you know, assuming V naught is 0, then V is equal to Q over the capacitance. Yeah. Now the Q is changing. It's the thing that's, you know, it's changing, and capacitance is a constant. The C is constant. The Q is now, again, this is during the time when it's adding up. Right now, we've kind of assuming that the thing was fully charged, but this is during that time period when it's actually charging up, going from 0 charge to maximum charge Q. and going from zero potential to maximum potential delta V. Okay. So that's when this mathematics is taking place. And so we substitute in equation 11 into 9, and we have that the work done to charge of the thing is equal to, I'm going to keep the one capacitance, well, let's do it step. So integral of Q over C dQ, but the 1 over C comes out because it's constant, so the work is equal to 1 over C, the integral of Q dQ. Excuse me. All righty. So let me have you do a little work here. I want you to finish the problem. Finish the integral. You finish the integral, you're going to get a solution. That's going to be your first basic, and then substitute. And then once you do that, go back and substitute in the general definition of potential energy, because we generally do this in terms of potential energy stored in. So this is the work done in an ideal case with no losses to heat or anything. The amount of work that is required to store the charge is going to be equal to the total potential energy in the charge. And again, the analogy is just like, you know, I have a mass at a zero potential energy point. I do work to pick it up. How much work is in the thing? Well, the total potential energy it has at that level. The work is going to be converted to stored potential energy, gravitational potential energy in that case, in this mass system being the Earth and the whatever. Here, same thing. How much total energy is in? It's going to be the work done to push the charge around and put it on that capacitor. So finish the integral, then use the general definition of potential energy to write the solution in terms of potential energy. But then traditionally, there are 3 ways we can write that equation, and all of those ways, it's kind of looking at the energy from 2 or 3 different perspectives, okay? And see if you can, and we can use we go back to use the definition of capacitance in order to get those other 2 versions of the equation. So you integrate, get the one version using general definition of potential energy after you finish the integration. Then use the definition of capacitance to manipulate that one equation to get 2 more versions of the same equation. Do that right now. Take about 2 or 3 minutes to do that. Oh. So how are we doing? Did anyone get a solution? Oh yeah, no worries. So Bron, what's the what is the work required to charge the capacitor? How much work is required to charge? The final answer in terms of charge and capacitance, in terms of the total charge of the thing. And remember, this is not, you can think of this as not a definite, as not an indefinite interval, right? It's or a definite interval. The charge goes from Q equals 0 when the thing is not charged to the maximum charge on the capacitor, which we said was Q. So you can think of it as a definite interval. And so what do you get? What's the integral of Q dq?
Q squared.
Nope, not quite. There's a constant there. Well, there's a factor there. We can assume the constant is 0. Not quite Q squared. All right, the integral of x to the n dx. What is that?
Wait, what was the first variable? X squared?
No, x to the n. It's not. It's the integral of x to the n is not. Well, in your the analogy that you said, Babatunde, would be x to the n plus 1. That's not true. Oh yeah, thank you, Bron. Yeah, it's this. It's 1 over n plus 1 times x to the n plus 1 plus a constant. So back to you, Babatunde. So then what is the integral of q dq? Well, Bron told you, but I mean, you there, Babatunde?
Yeah, I'm here. I'm sorry.
Yeah,
Yeah.
it's 1/2 x squared or 1/2 q squared. You got the 1/2. That's what I meant.
Oh, okay, got you.
I mean, that's a big deal. That's not like that's like you can't just forget that, right?
Yeah, forgetting my
Yeah,
basics. Yeah,
yeah,
my apologies.
yeah. Go back and review that stuff a little bit. Yeah. So what we have then ultimately we take the integral, we get the work is equal to C, and then we have 1/2 Q squared from 0 to Q. So then the work done, charge the capacitor is equal to C times well, we could do like this. So 1/2 Q squared over C. Okay, so that's one equation. And they all have different interpretations. So this form of this equation would be is the work done by the battery to charge the capacitor. So that's what we could call this. The work done to charge capacitance. Okay. Well, now, if the capacitance is equal to the definition of capacitance, gives us, we can use that to get different perspectives. All right, the definition of capacitance, remember, as capacitance is equal to charge over voltage. Now, I'm not using a delta V in that case because I'm assuming that the delta V is 0. I'm applying that specifically to this problem. So if I substitute, so which one I want to go with first? Let's substitute. So let's solve this for charge, and yeah, let's do that one first. So let's substitute for charge, and we're going to get that the charge is equal to C times V. And if I substitute 16 and 15 and do the algebra, then I have that the work is equal to I'm going to do two things. I'm going to say that if I assume that the right side I'm going to manipulate with this guy, but the left side, that's where I'm going to do what I asked you to do, which is use the general definition of potential energy, which remembering that the absolute value of the total work done is going to be equal to the change in potential energy associated with the capacitor. And of course, if delta W, well, yeah, right. The work done is equal to the change in potential energy. But if the initial, like if going back to this relationship here, delta V is equal to delta U over Q, but V is equal to just U over Q, right? Because if V initial is 0, then U initial is 0. So this just becomes that the work done is equal to the total potential energy at any given value of charge or any given time as you're moving through. So if I substitute 16 and 17 into this guy, then I get a different form of this equation, which is that the internal energy or the electric potential energy stored in the capacitor is equal to 1/2 C squared times V. And again, it's all the same energy, so I'm not throw you off, but what this is kind of looking at the energy in terms of the stored internal energy. So this is the work done by the battery to charge it up, this form. This form is the total in store, the electrical potential energy stored in the capacitor. Stored electrical energy or electric energy. And the interpretation here is how we can think of this. If you were to actually look at the average potential difference across the battery while it's being charged, that at the it's going to be equal to 1/2 times the maximum potential. Yeah, it'll be like a delta function. And so one interpretation is that, you know, like the stored internal energy is equal to the square of the capacitance times the average potential of the capacitor during the charging process. Yeah, so that's one way to kind of think about that. And we've got one more version. We can solve this for capacitance and substitute it in the, no, solve it for both, solve for what? Let's say we have, no, I'm sorry, that's not the one. This is, my bad, that's not this one. This is different. This is a different point of view. This one is, yeah, right. Scratch what I just said. That's not the interpretation of this form of the equation. The interpretation of this form is it can be related to the energy stored in a spring. Remember that whenever we looked at a spring, it takes work to stretch a spring, and the amount of work to stretch that spring is equal to the potential energy inside the spring. And we did that last semester. A spring is considered a conservative force. So the, you know, and that was the kind of point of view that I had started doing this. You could do this integral a different way, but you know, work is equal to F, integral of F dot dx. Remember that? But F for a spring is equal to negative K, basically X. Taking the absolute value, F is equal to KX, right? So if we take that substitute in here, the work for a spring, Hooke's law, is equal to the integral of Kx dx. It's the same kind of integral almost. So K comes out, right, X dx. So then we get K is equal to, you know, work is equal to 1/2 X squared, right? When you know, like go from 0 to maximum displacement. I don't know what you call it, X, whatever, you know, you get what I'm saying. So it's like you have a spring, it's on a wall, right? At equilibrium, X naught, but then you stretch it through some distance X, right? Well, it takes work to pull it out. The work that you've done is equal to the potential energy in now, because the same kind of thing, right? That work is equal to the change in potential energy. We substitute these in. So the total internal energy of the spring is 1/2 Kx squared. All right, let's look at these two equations here. I gotta give some. Let's compare these equations describing the potential energy of a spring system and that of a capacitor. So the potential energy is equal to 1/2 K X squared. Remember that formula? So if you can compare these two, let me give numbers here. So 19, 20, 21, 22, 23, 24, 25, 26. If you compare 26 and 18, you see that there's some mathematical analogies. The X is like the potential, the electric potential. Is that the one? No, I'm sorry. It's sorry. It's comparing. You know, this is Monday morning. I'm sorry. It's comparing equation 26 to 15. The X is like the charge. That's what's changing as you stress the spring, and that's what's changing in the capacitor as you charge it up. So the X is analogous to Q, and the K, the spring constant, is analogous to the 1 over C. So the larger the capacitance, or the larger the 1 over C, the harder it is to charge the capacitor, in the same way that the larger the K value, the harder it is to stress the spring. So it's the inverse of capacitance. That's, yeah. So, and don't let this through. I could also write that, in terms of U here as well, right? So don't let that throw you off. So one version of U is that it's equal to 1/2 Q squared over C. That's analogous to the spring thing. Another version is 18. That potential energy is 1/2 C squared times V. Now that interpretation is the work required to charge. Yeah. Yeah, that's the average potential thing I was just saying. So that is true. So it's just kind of thinking, it's saying the potential energy is equal to the square of the capacitance times 1/2 V, but it's like 1/2 V is the average value of potential difference as it charges up. So yeah. And then finally, I can do it's just the last version of this. We can substitute. So here I substitute C into that. I substitute Q. So this is what I put in to get this guy. But if I substitute C directly into that, then what I get is that potential energy is so. I don't know why I'm getting this kind of dyslexic. C is equal to charge over voltage. So if I take that and put it into 15, then I get the final version, which is that the potential energy is equal to 1/2 Q times V. So that's another way to think about this. So all three versions of these are valid versions. Oh, something good. Yeah. Well, those are the interpretations. I think in particular, these equations show you that, as in this case, if you could connect the capacitor to a fixed voltage source, which this is DC, so we're assuming that the battery has a fixed voltage. So it shows you basically that, you know, the capacitance, first of all, the capacitor has the ability to store both energy and charge. For a particular amount of voltage. We can see that like in any of the particular equations 28 and 18. You know, for a particular voltage, then you know, the amount of charge and potential energy stored in that charge associated with that stored charge is going to be, it's going to be determined. So yeah, I mean, even just looking at the definition of potential of capacitance here can show you that. If you have a fixed battery, then for a particular capacitor, you're going to have a certain amount of charge. But if you increase that capacitance, then you increase the amount of charge that's stored, right? If you have for a particular, so you have one, you just have one battery, but you have two different capacitors. In that equation, Q is C1 times V or delta V, and then Q1. And Q2 is going to be for the C2 times delta V. Well, for the same battery, if C2 is larger than C1, then the total amount of charge stored, Q2 is going to be larger than Q1. And then looking at equations 28 and 18, you see the amount of stored energy is going to be larger as well. Okay, so that's the way to think about it. Now, for equation 15, the original one, that perspective is you might want to send charge. Like once you have a capacitor, you can take the capacitor and do stuff with it. As I told you, you can take it out of the circuit, use it for whatever. And again, you can think of it as stored energy or stored charge. But let's say in terms of equation 15, if we're thinking about it as stored charge, and we want to send that charge from one conductor to another, whatever, I don't know. Or maybe it's in the circuit and it's doing something funky, but whatever that circuit is doing, it's dependent upon charge being transferred from one place to another. Well, this equation gives you the perspective about that in terms of the capacitance, because it tells you that it's essentially the amount of charge is in, well, the energy is inversely proportional to the capacitance, but basically it's saying that it's easier to send charge from one conductor to the other if the capacitance is, how do you say that? the larger the capacitance, the easier it is to send charge because it's the energy transfer is equal to 1 over the capacitance. Yeah. Right, it's equal to the inverse capacitance. So the larger capacitance, the smaller the inverse of the capacitance. So the way I think of it is this. That might be a little bit see it how you get that mathematically from here, but basically, if you're kind of looking at these equations, we know that this potential is energy per unit charge. So for a particular capacitor, like in this case, C2 is greater than C1. Well, for the how, how, which capacitor do you think will require more work in order to charge? The one with lower capacitor or higher capacitor? Well, if you understand that potential is proportional to energy is proportional to work, then basically the battery has to do more work to charge the capacitance that has a higher capacitor that has a higher capacitance than a lower capacitor, right? So it takes more work to charge C2 because C2 is greater than C1. Well, now once those two capacitors are charged and you take them out, then and you're using that one has more energy, so it's going to be easier to dissipate that energy from that capacitor because it has a higher capacity. It's almost like going back to the analogy of the hill. Remember, if the battery, it basically takes it creates a potential hill in the circuit. But the capacitor is like a regulator of how steep that hill could be. So if you have a higher capacitor for the same battery, like if let's assume these are, this represents C1, and that has nothing to do with length. Let's assume that these two things are the same length. Well, this has C1 and this has C2. If I could hook the same battery or a battery with the same potential, ultimately, they will create hills that, relatively speaking, look like this. C2 will have a hill like this. C1 is less, right? So when they're fully charged, this one has more energy than this one. C2 has more energy than C1. Now, when you take they're fully charged, you can take those capacitor out and treat them like components to do other stuff. Well, now you've got one C2 has more energy in it. So when you put it in, the charges are going to flow off faster in whatever you're putting it in than off C1. Why? Because it just has more energy, but analogously, its hill is steeper. All right, so that's really what this equation is kind of saying. All right, the inverse in the capacitance gives you a lot. If the capacitors are larger, now that energy flows off easier than for a lower capacitance. Yeah. So that's it. Those are all the different interpretations of what these equations mean. I hope that makes sense. I actually don't think Halliday and Resnick do a great job of, they do a good job of going through the integral, but I'm not sure they do as good a job as explaining that. But one book that does do a pretty good job is the Zemansky text, the one that we used to use as the source of this, as the text of this thing. So, but I'm sure you can look it up online, and they'll talk about these different interpretations of these equations. You can Google it, and it probably would find it somewhere. But I hope that helps a little bit. Any questions about before I finish out with energy density? We good? Cool. All right. So let's now talk about energy density. I told you that you could think of the charge of the energy as being stored in the field. Actually, none of these equations really show that. This just energy associated with change in potential and work, ultimately, and charge. So, but I do like this analogy of comparing it to a spring. But again, that's really just focusing on charge and electric potential. Doesn't really say anything about the field. So energy density gives basically a fourth interpretation of how the energy is stored. And we can think of it as not on the charge, but in the space between the capacitor plates where the field exists. So energy density. And why a density? Well, you know, density, you remember from mass density, it's like this mass per unit volume, because mass is contained in a volume. Well, in the capacitor plates, that's the space between the capacitor plate is also a volume. If it has spacing D, that's a side view, remember. But like, you know, a kind of a three-dimensional view would be something like this. There's one plate that goes on, and then there's the other plate. Right? And the electric field, you know, is inside that volume, right? Well, if the separation of the plates is D, and if the cross-sectional area is A, then the volume associated with, I use a little hat on my V to represent volume to distinguish it between voltage. So that's the way I write voltage. This is the way I write volume. So V is equal to A times D. And that volume is occupied by the electric field. So an energy density, and I'm going to use symbol U for energy density now, is energy, it should be is energy per unit volume, right? Energy density, you know, mass density, mass per unit volume is mass per unit volume, the energy density, and the symbol we use is like a little u, small. So capital, large U is, it's kind of hard to distinguish between these things here, but large U I'm using for potential energy, and small u is energy per unit volume. So we can put a little like curly Q or something, like small u. So the energy density is equal to the total energy divided by the volume. Okay. So basically we can plug and check. Now the way I'm doing it, since I've already derived, integrated the energy, I can just substitute it in. I'm going to use equation 15. But you might see other ways of deriving this as well. You can derive it from base principles in which you would integrate, kind of incorporate. In other words, you could put it in here, right? Like I did this in terms of, well, actually not in there. You can derive this another way, just starting basically from energy, an infinitesimal, a differential amount of energy in the thing. You might see that somewhere, but we don't have to do it that way because we've already integrated and figured out what the total energy is. So we can just use that maximum value. In other words, clearly, before I charge up the thing, the energy in the place is 0. But I can think of figuring out the total energy just from using energy density. You can actually do that. The concept of energy density and charging it up. Anyway, I'm not doing it that way since we already have the total amount of energy. I'm just going to start from the definition of energy density, and this should be 3 equal signs. And now that I have the maximum energy, I can kind of just really just substitute it in, but I can do a little work. So starting with the equation to figure out what the total energy density is for that, let's start with equation 15 over there. I need some space. So let me erase. Yeah. Starting with 15, the energy, let's keep the numbering going here. So this is, I'm sorry, what number did I end up with? Was it 26? What was the last number I had? Anyone know?
You're up to 28.
28, okay, so this will be 29. So rewriting down 15, but strictly in terms of energy. Energy is equal to 1/2 Q squared over C. So that's the maximum potential energy in space. But I can write that in terms of field. And how do I get to that? Well, I've already determined, we used Gauss's law at the beginning of this chapter to figure out what the electric field is, E, in between the plates. And we did that in terms of, I'm sorry, we did a couple things. We know that we can write, there's a relationship between electric field and the potential difference between the plates. But we also determined the capacitance of the thing in terms of geometry, right? We said that the capacitance is a purely geometric quantity, is what we said. So that for a parallel plate capacitor, the capacitance is equal to epsilon naught times the cross-section area divided by D. But we also know that the relationship between the potential difference and the space is, you remember, like delta V is equal to negative integral of E dot DL or DX. And in our case, then we can take the absolute value, so absolute value delta V, and do the integration. And it just becomes, for a simple thing here, it's E dot, basically delta X, but delta X is the symbol, is D, right? Or E, X from 0 to D, which is just E, D. Okay. Oh, sorry, it's not that one that I'm going to use. It's actually 18. I need to use for this. Sorry. So not 15, 18. That's the one we want to start with. I mean, you could do that. You could start with any of them actually, but I want to start with this more straightforward just to get to the answer. I'm going to start with this. So sorry about that. So C squared over C squared times V is what I'm going to start. It's all U, right? All the same energy, so I can start with any one I want. But starting with that one, so that's from 18. I can substitute 31 and 32 into 30. Straightforward. So 34 then, and we're going to get that the energy is equal to 1/2. Now the C is this thing, so that's going to be epsilon naught A over D squared times delta V, or V, which is E times D. Okay. And so then I guess we just have a bunch of algebra, right? Or did I do that right? Oh man, what's happening here? No, it's not that one. It's the one I just erased. The last one. Folks, I'm so sorry. I don't know what's wrong with me today. I'm just completely out of it. It's the last one, not this one. It's not. This is not going to get it. It's the last equation that I just wrote down, which was the one with V squared in it. Where's that? It had to be the last one that I wrote. C times delta V squared, 1/2 C times delta V squared, right? Yeah, so sorry. So not 18, but whatever. What was that, 20? Was that the 28, equation 28, Babatunde?
Yeah, 28 was half Q times V.
Really?
You know what that was? I remember 27 was C equal to Q over V, and then you had U equal to half QV.
Oh man, yo, I did an algebra mistake. The square is on this guy. So sorry, man. Jesus. I did it in my head, and I just messed up. I don't know. I just wrote it down. Right. When I take C, Q, and substitute in here, I'm going to get C squared, V squared. The C squared will cancel the C on the bottom, so I'm just going to have C on the top, and I have V squared there. I'm so sorry. So it is that one, but I wrote it wrong. Right? It's 1/2. I think it's just one of those days. 1/2 C V squared is actually that equation. And the 29 was not wrong. That was right. That was 1/2 C times V. So the three equations are 1/2 Q squared over C, 1/2 C V squared, and 1/2 Q times V. Those are the three equations. One half Q squared over C, 1/2 C V squared, and 1/2 Q times V. Those are the three equations. Is that what you have? So fix this, and that's what that. So what did you say the last one was, Babatunde? It was 1/2 Q times V, right?
Yes, 28.
Yeah, 28 is 1/2 Q times V, 1/2 C times V squared, and 1/2 Q squared divided by C. Those are the three. Ugh. All right, so yes, it is 18, but written correctly, it's the potential is squared, not the capacitance. Everybody got that? So sorry, I don't know what's wrong with me. I think maybe it's the election or something, I don't know. By the way, in California, you can still vote. You can register on the last day, so don't let that, people tell you can't. You can. You can even up to tomorrow. You can register on but certainly on the day of, because you can register in California. You can register on the day you vote, so you can still do that if you haven't. And if you haven't voted already, vote. So now let's do the algebra again. So 32 and 31 go into this guy. So 1/2 energy is equal to 1/2 C. I guess that's what was throwing me off. I knew something was wrong. I couldn't figure out what was going on. That's why I should never do anything in my head. I just can't. I don't know. I've had that problem since I was 6 years old. I don't know. Just make little errors like that. So frustrating. Anyway, what are we doing? We are plugging 31 and 33 into 30. So C is 31. That goes here. So that's going to be epsilon naught A over D And 33 is that the voltage potential is equal to ED. That goes in squared. So I have E D quantity squared. So now it's algebra. So we're going to get the energy. It's 1/2 and epsilon naught A D. And over here we have E squared, D squared. One of the D's cancels. So D goes out. Over here I'm left with 1. So the total energy in between the plates then is 1/2 epsilon naught A times D times E squared. Okay. But let's have a look at it. Worked out this weekend. Sore. Or I'm just old. Both. A times D is the volume. I just pointed that out. So I can volume is equal to A times D. So total energy is equal to 1/2 epsilon naught times the volume times the square of the field. And so then dividing the whole thing by the volume, I have that the total energy divided by the volume is equal to 1/2 epsilon naught times the square of the field. And the definition of energy density is that it's total energy divided by total volume between the plates. So here we have the energy density stored in an electric field of a capacitor is equal to 1/2 the electric that permittivity times the square of the field. So energy density goes as the square of the field. That's a big deal. Now, why do we go to the trouble to do that? It was because you can't really compare energy, right? Like, yeah, the actual value of the energy is kind of relative. You know, maybe the thing is not fully charged. Yeah, I just showed you too. Like it depends upon the battery. You know, you could have the same. You know, like here when I made the analogy of the same battery in different capacitors. What if you have the same capacitor in different batteries? Well, clearly you're going to have more energy stored in, and that has nothing to do with the capacitor, but everything to do with how much energy you put in the first place, right? So it doesn't make sense to compare capacitors in terms of the actual amount of energy that's in the thing. You know, it's kind of like you have 2 buckets, right? You got a 5-ton bucket and you got a 5-gallon bucket and a 1-gallon bucket. Well, sure, the 5-gallon bucket can hold more water potentially, but what if in the 1-gallon bucket you've got a gallon of water, and in the 5-gallon bucket you've only got a half a gallon of water, right? It doesn't say really anything about the barrels. So the more reasonable thing is to talk about the energy per unit volume that could be in the thing. That rates the I don't know, ability of the energy that can be stored better, for example. So that's why energy density is important. Yeah, that's it. Yeah. So, yeah, I think that's it. All right. Dielectric, very fancy name. Does anyone know what a dielectric actually is? We'll talk about what it does. That's what this section is about. But does anyone know what it actually is, what it's made of? Or heard that term before? Anyone? You have electric kits when you're a kid, or well, it's pretty simple actually. It's not dielectric. If you have a, let's just look at the capacitor plate here. So we have a capacitor plate. We'll compare capacitor plate with a dielectric and without. Okay, so I've got a voltage across the capacitor. We'll call it V naught. We'll call it the potential without the capacitor in it. So I've just kind of taken it out, right? You know, like I know it's in a circuit, we get charged up. I need to draw that. So it has charge and it has a certain potential across it. Okay, and remember, you can kind of visualize the charge in the following fashion. Positives on one side, right, on the surface of the thing, negative charge on the other surface. And yeah, there's a field in between and all that. We don't have to draw all that. Well, okay, sure, why not? And yeah, you do have to make that noise when you draw it. And over here, we have another capacitor, and we're going to put a dielectric in it in a moment. We'll call that voltage just V. Now, a dielectric is essentially a piece of plastic. It can be some sort of composite type material, whatever, but essentially it's just plastic. I before E, except after C. Let's do space. So it's no complex thing. Now, presumably, this thing's charged in V naught. It has a has a positive plate and it has a negative plate. And we know that the total charge on the plates is Q, and we've looked at all the stuff of how energy and everything is stored. But check this out. There's a field between here that's permeating the space, and we're assuming that when there's nothing in between the dielectric, it's it's just a vacuum. But if we take a piece of plastic and construct it such that its volume is just slightly less than the volume of the dielectric, or the volume of the space in between the plates, such that we can snugly put the plastic in between the plates. Just kind of slip it down in there, and so it's a rectangular piece of plastic of volume D, where D is the separation of plates times the area of the plate. Then let's evaluate just qualitatively what happens to some of these quantities associated with the capacitor. I'm stick my dielectric right in here. Okay. Now, ACL. Let's first start with the field E. What do you think happens to the field E whenever I slide my dielectric down into that volume, assuming that the dielectric is just essentially an insulating, like a piece of plastic? What happens to the magnitude of E? Just based on your personal experience, or your logic, or your intuition. You warm up my tea while you're thinking about it. Don't overthink it. It's not there's no trick questions here. Braun. Interrupted or changed, and Braun says it gets loopy. Okay, loopy. What physical? How does it? How? I don't even know how to ask the question. Well, I'm not sure what loopy means, but let's go with what ACL's is that it's interrupted or changed. So agreed, it's definitely interrupted or changed. Still gets loopy. Like maybe you see positive charges where there probably should be not be. We'll get into why what's happening is that has to do with why we have to kind of look at it internal. And maybe you've read ahead, just cool. And yeah, if maybe loopy would be a good description, and we'll come back to that. That's a judgment call. That's a value judgment, though. Let's specifically talk about what's actually happening. But we don't even have to know anything about that, about what's happening in terms of the charge in the, on the thing, on the plates, whatever. We'll get into that in a minute. Just don't overthink it. It's a piece of plastic, right? And the electric field, well, we actually, I kind of gave you a hint. I said in your experience, well, we actually do experience, right? We experience it. You're experiencing it right now when you're using this Zoom. How can we communicate and, we're miles away from one another? What's actually being communicated? What's actually, is being sent or being, what is the physical quantity that's causing us to be able to communicate? It's an electromagnetic wave, which effectively is an electric field. I mean, it's a little bit more, it's not, here we're just dealing with electrostatic fields, and electromagnetic wave is a combination of electric and magnetic, you know, and they're out there doing a bunch of stuff, which we'll talk about in a few chapters. But the point is, it's just an electric field. That's all, it's just a field. And we know what happens to the signal of a field when we go into things that are, you know, large kind of insulators like concrete. What happens when you on your phone and you walk into a concrete building? The signal definitely changes, but you can be more specific into that. Change, what does that mean? Increase, decrease? What happens? What happens to the signal? It decreases. That's what I'm looking for. Yeah, decreases. So this field, it's harder for it to get through here, right? So I'm going to draw a dotted line, meaning, and I guess really, what I really should do is make, because we say the number of lines, the line density represents field strength. So if over here the field looks like this, well, over here maybe the field is, you know, it's like that now. Yeah, it's a better representation. It's line density. Yeah, the field decreases. What about the electric? So yeah, let's say that. So just based on our intuition, we'd say that the electric field should decrease. Placing a dielectric in between the plates causes what E decreases. In fact, why don't I make E naught, like all the naught quantities are the values of the quantities before I place the dielectric. So mathematically, we could say something like, and well, maybe we should write it too, just whatever. So E decreases so that E should be less than E naught. What about the electric potential? What happens to the potential, you think? Does the potential increase or decrease? Well, what's the relationship between E and delta V?
It decreases as well.
Yeah, it's wonderful, right? We just said that, right? Delta V, for a constant field, delta V equals ED, if D is a separation of the plates. And so the potential decreases as well. Wonderful. There's a lot we can know just from logic and intuition without getting all loopy, as Braun put it. Yeah. So that's electric field potential. What else? What about charge? And remember, the charge is on the plates, and it's excess charge that's come from, you know, how we talked about. We won't get back. We talked about that at length. So we know they're electrons, and property of, you know, excess charge is that no excess charge and it can exist inside the conductor or no field. So what happens to the charge? What do you think happens to the charge? Increase, decrease, what? Now I know what you might be thinking. Like when I say I plate this dielectric in, right? It's kind of, you know, snug, but it's not so snug that it can. There's charge on the plates. Like it's not going to really. Well, you tell. I mean, there's no mechanical problem. I can put it in. You know, I can just slip it through, and just putting it. The physical act of putting it in doesn't necessarily affect anything. If it affects it, it has to be from some physical interaction, not a mechanical, just I'm sliding it on. It's not like static charge, right? Where, because this is a metal, right? So, and this is a piece of plastic, so there's no problem with that. Or you could even think that it's say it's snug, but it's so close, but it's not actually touching the side. I don't know how you would think, however you want to think of it. It's an ideal situation. So what happens to the charge? Anybody? Take a stab. Just guess. Oh,
It
Bron?
stays the same.
All right, so Babatunde says it stays the same. Oh, the question is what happens to the charge, Bron? And yeah, Babatunde, yeah, why do you say it stays the same?
Because there hasn't been anything to negate the quantity of charge. So although they might move differently, maybe at a different rate, I assume they will still be the same quantity.
Okay, good. That's right. But what are you talking about moving? What's moving at a rate?
Well, I guess it's defined by the potential, the rate at which it moves from one plate to the other across the dielectric. I'm assuming it's slower with dielectric present.
Okay, okay. Well, who said anything about charge moving through the dielectric? And who said anything about charge moving at all? Like, when did we say charge? What gave you the impression that charge moves across the space, whether a dielectric is there or not? Where are you getting that from?
Well, just like it would move in a regular setup for a capacitor.
Again, let's go back to that. When did we say that? You mean moving across the space of the, like charge moving across the space between the capacitors? That's what you mean?
Yeah, yeah, like basically moving from one plate to the
One plate
other.
to the other.
Yeah.
When did we say it did that? Now, you're talking about across the space. Like when you say move from one plate to the other, what do you mean? Braun? We'll get to that in a moment, Braun. Babatunde, let's clean this up real quick. Let me just help you.
Yeah.
There is no time that I ever say or imply at or anything that charge is moving across the space in between the capacitor from one plate to the other. I never said that. Never even implied it. What I said is that in the wire, when you connect the battery, you can think of charge being pulled off one plate and going through the circuit to the other side. I did say that. That's one way of thinking about it. Now, what I really think, and that was just for an illustration, what actually happens is more like the board, going back to the Star Trek analogy. A negative plate charge leaves that plate, but then right over here, one jumps onto this plate. And they can do it because they're all connected. It doesn't have to be that one charge runs around the battery. I talked about the thing flowing down the potential hill. That's just an analogy. It doesn't actually roll down a hill or roll around it. Like that's an analogy to understand, but it doesn't really move in that sense, charge. We talk about it, we're going to talk about it flowing like a current. All that's an analogy. It doesn't really do. I don't think we actually fully know, actually. In fact, there's some people that speculate, there's some train of thought that say we don't even really understand what charge is, that it's not really the model that we say. And that's changed. That's changed. Over the past 100 years. It changed more so in the first 25 years, from 1900 to 1925. After 1925, we kind of all agreed on a certain thing, and that's what I'm teaching you. That charge is a monopolar. But there's some people that say that we don't really know, that it's not, that there's something we've missed about what charge is, which is why we don't understand gravity. But that's that's for talk about next semester in 39, at the end of the course, by the way. But just to say that, like, that's the analogy that I gave you, right? But I never said anything about any charge moving across the space. In fact, what I said, because the other analogy I talked about is positive charge flowing onto the capacitor. That's another way you can think about it. It's another model that is not really negative charge being pulled off, but there are positive charge flowing, onto that plate, right? Which is really holes, and we talked about all that. But I never said anything remotely about something jumping the space of a capacitor. Braun, if field decrease doesn't get used, or rather our measurement for the charge is different. Well, that's the point that I'm making here. Good. You might think that, right? You might think that because the field decreases, and we know. But again, it's a physical thing here. Like once these charges are on the plate, they are the origins, and they're the monopoles. The charge starts on the field charge starts on a positive charge and ends on a negative charge, but the field is not the charge. But we definitely know from your intuition that the field can diminish, because it's the same thing that happens when you go into a place where there's stuff like concrete, that the signal coming from the tower or from a satellite has to go through the building, really, and that's why it gets weak. It's just that, and we haven't talked about why, but using that analogy, right, of your analogy. Now, yeah, maybe there's charge and stuff, like we haven't talked about what generates an electromagnetic wave, but it doesn't have anything to do with this building. It's coming from someplace else. So when you're on your cell phone and you walk into a building and the signal weakens, essentially what you're suggesting, Ron, is somehow, because that signal is weak, it's affecting the charges in the device that the signal is coming from, which could be miles away on some tower someplace. And even that's transmitting a signal from it could be coming from a satellite. Why would that have to do anything to do with the charges that are oscillating up there in that? You see what I mean? So when I place this dielectric in here, it's not really associated at all with the charge. The charge is on the walls of the capacitor. I mean, let me make it a little bit easier for you. What if I did something like this? Because I could, that the capacitor doesn't really have to, it doesn't have to take up the whole volume of the thing, right? I might make some kind of dielectric, not the capacitor, but the dielectric, that looks like that, where it's actually skinnier. The volume of it is much less than the volume of, but still the field has got to pass through the thing. Do you think that would still affect the field? Yeah. And now I'm not even remotely close to the charge, relatively speaking. So there's no reason that placing that dielectric in the plates, in between the plates, should affect the charge on the plates, no more than the fact that you get a diminished signal when you walk in a building should affect the charges or the oscillating charge, in the place where your electromagnetic wave signal is coming from. I mean, it doesn't even know that thing doesn't know what you're doing. It has nothing to do with you. It's just putting out a signal. You could kind of think of the field for the charge on the capacitor plates in the same way. They might not even know there's a dielectric in here. I don't know. So for that reason, I agree with Babatunde that placing a dielectric inside here doesn't affect the amount of charge on the capacitor plates, although the field does diminish, which means that there must be another reason that the field diminishes in the dielectric, and it must have everything to do with the dielectric and nothing necessarily directly to do with the charge on, or more specifically, charge in the dielectric, because it does have charge, even though it's an insulator. It doesn't have any free charge, but it's definitely got charge, right? But nothing to do with the excess charge on the capacitor plate. So charge stays the same. And here we're talking about excess charge on the capacitor. That's what I mean by charge. So the excess charge or just charge on the capacitor. It's not affected. So we just say Q naught just stays the same. I'm not even going to write another Q just so as to Q naught is, in fact, let's make this Q naught plus Q naught negative. See, it'll be the same over here. All right. Ooh. Mm-hmm. So I want you to do something, and I need to take a quick break. Some medication. Let's see if you can derive these things. So we established something called a dielectric constant. A dielectric constant is the ratio of the change in potential difference. It's a unitless number. The ratio of potential difference before and after the dielectric is placed. We use chi, the symbol chi, I think it's KAI. And chi is equal to V naught divided by V. So it's going to be a number greater than 1 because V naught is always greater than V, right? For the reasons we just mentioned. And that's called the dielectric constant. Okay, so what I want you to do is see if you can use that to derive, and everything we've just done to derive relationships for E, C, and the energy, the electric field, the capacitance, and the energy in terms of the dielectric constant. See if you can work on that a little bit, and you probably see this in and then I'll come back and clean it up. So find E, C, and U in terms of chi. See if you can do that. And the big question is, which we haven't asked is, think about to yourself, what happens to in the same way I kind of walked you through what happens to the potential and to the field, think about what must happen to the charge. Think about what must happen to the capacitance and the energy based on placing the dielectric in. Then see if you can write those last three in terms of chi, given that chi is equal to the ratio of the potential. Go ahead and see if you can do that right now. Right back. Anybody get in? Like an insulator for the field and voltage, BRB. I don't know what BRB means. And yeah, maybe. I don't know. I get what you mean. I wouldn't use that term like an insulator for but yeah, maybe. Yeah. I see what you're trying to say. Like heat flowing through something, it insulates. Yeah, I see what you're getting to for like that. But remember, voltage is not a, insulation implies some sort of direction. That's more like, well, heat is not a vector either. It flows. Potential, I don't know if we could say it flows, but um, yeah, I don't know if we could say that, but definitely the electric field has a direction. So yeah, maybe an insulator for the field, not so much the voltage. The voltage would just be maybe affected because the field changes. Um, but yeah, what does BRB mean? Hmm. Anybody come up with the first? Let's do E first. Anybody get that? It's only a couple steps, not very difficult. And we already know that E decreases. I just want to write it in terms of K. How would you do that? Anybody? Oh, be right back. Okay. Julia, did you make any progress with that? Or ACL? No? Anybody? What electric field equation? But there's no find it for a capacitor. So direct the relationship between capacitance and field. So when you say find it for a capacitor, find what for a capacitor? I mean, you're warm. I think you're kind of warm, but did you do it? Did you get it? Do you have an answer? Like for you, it would be. I see. No, not quite, not quite, because it's the energy is the other way around. You get it from the energy equations. No, uh, because it's you have to think about like the hierarchy of what's happening. The field diminishes, so the potential changes. If the potential changes, the energy changes. So um, I'm not sure you can just take the total amount of energy and then substitute something like that into it to get the thing. I'm not sure that was. I see where you're going with that, but I'm not sure that that's. And I guess I'm trying to think logically why that's not a reasonable way to do that. Right now, I'm not thinking of probably because it's not linear. There's two different relationships. Probably, yeah. That's probably how I would say that. Because the relationship between field and potential is linear. And the relationship between energy, that's why it doesn't work. And the relationship between energy and field is quadratic, right? The energy goes as the square of the field. So that's why you can't do that. No, that's not why. It's why you can't just plug it in like that. Let me help you. So it's actually this relationship here. Right? If you look at the two, right? So you have without the dielectric, you have E naught is equal to V naught times D. Now remember, D is the separation between the plates. That also doesn't change. I didn't think I had to say anything about that, but you know, that's D. That doesn't change it. You know, we're not physically changing anything about the plates. So that's one equation. And then another one is E is equal to V times D, right? So that we can just divide the equations. We divide them, the D goes out, and we get something. If we want to write it in terms, yeah, so we can just multiply. So we have E naught over E is equal to V naught over V, or we want to solve for E in terms of E naught. So we get so that's the same as E over E naught equals V over V naught, so that E is equal to E naught V over V naught. But this guy is 1 over chi, so we can say that E is equal to E naught divided by chi. Yeah. And chi is going to be greater than 1 because of, you know, V naught is always greater than V. So that means that E is always going to be less than E naught. So that's the kind of thing I'm getting at. Now that may be what you were trying to say. But do it in terms of the linear equations, right? So all these definitions, like this is not really a definition, but it's a relationship of delta V to E. But you now have a relationship we have a relationship between potential and capacitance. And it's a linear, well, actually that's not linear because it's reciprocal, but kind of, you know, like, I guess it is a linear relationship, like where the proportionality constants, if you, the relationship between charge and potential is actually, yeah, the relationship between capacitance and charges. Well, you have the definition of capacitance, that's the point. So use that equation and see if you can do something similar to what I did here to see how the capacitance, see if the capacitance changes, the capacitance of the thing with the dielectric as compared to the capacitor without the dielectric. Take a minute or two to see if you can do that.
Excuse me, Professor.
Yes.
If E naught is equal to V naught D and E is equal to VD, wouldn't E naught, E over E naught be, oh, okay, I see it. Okay, I'm sorry. I was thinking it was E naught over E. Okay. Huh. EV.
Yeah, that arrow part over there, I flipped it around because I wanted to solve for E. So this is not an equal sign, it's an arrow right here, right there. So I took the reciprocal of everything, basically. That's what this is. Just flip it
Wow.
What?
Oh, no.
It's not that hard, is it?
I just had to take a while to see where everything was going, but I got it.
Oh, we only got 45 minutes left, so I'm gonna hurry this up a little because I definitely want to get to the circuit stuff. I don't want to spend 3 days on this. Try to finish up the day. So, I guess I'll start back over here. Capacitance is set as equals charge over voltage. So voltage equals charge divided by capacitance. So, and the charge doesn't change, right? So V naught equals C over C naught, if you will. And V equals the same charge over C. So again, you do the same thing. You can divide these two equations. So you're going to get V naught over V equals dividing by same as multiplying by the reciprocal, right? So you get Q over C naught times C over Q. Q's cancel. And remember that you said charge doesn't change, so there's no Q naught or, well, I guess yeah, let's just keep it Q naught. So we understand that that's the original charge on the thing, Q naught, because the knots go with the thing, yeah. So same over here, actually. I didn't write it on, but this is also Q naught plus NQ naught minus. So we have basically V naught over V is chi, right? That's how we defined it. It's usually chi is like some script. It's not just K, it's like a script kind of thing. I'm trying to draw it like that. And C over C naught. So C, the new capacitance, is equal to C naught times chi. So check that out. What happens to the capacitance based on this derivation? Ron, what happens to the capacitance? No, he walked away. He had to go someday. So Babatunde, what happens to capacitance?
It's directly proportional to K.
Yeah, but actually that's K is the proportionality constant. So we don't normally say that, we're comparing it to the other variable. Let me ask the question a different way. How does the capacitance with the dielectric in between compared to the capacitance with no dielectric?
It is going to be greater in magnitude.
It increases, that's right. it increases by a factor of chi. So that's how we want to think of it. And so that's huge. So basically, up to now, so what we've seen thus far, the field decreases, the potential decreases, the charge stays the same, the capacitance increases, which is significant. So it's a way to kind of manipulate the capacitance without, doing anything to the capacitor. So that's kind of a huge deal. It increases the capacitance. Now, don't get it twisted. We're assuming here that this thing, we're kind of looking at it now outside of a battery. Say we charge this V naught, we put it in the capacitor in a circuit, we charge it up to V naught, and then we could effectively, as I told you, open the circuit, take the capacitor out. And so you can manipulate this without it being connected to anything, right? So that's the context in which we're evaluating this. Because I don't want you to get confused, particularly when you consider the implication of what this means. We just said that the capacitance in the previous section, we talked about the capacitance, essentially kind of a rating. It determines how much charge you can place and how much energy you can therefore store in a capacitor. So if we're saying by putting a piece of plastic inside this thing, we increase the capacitance, then the implication is that we could increase the amount of charge stored. But don't get that twisted with the fact that this charge doesn't change because it's not in a battery, right? Like once you've charged it, that's the case. But if I were to take a capacitor with a dielectric as opposed to a capacitor without a dielectric and then put it back in that circuit, I could actually put more charge on it than if it didn't have the dielectric. That's a different scenario than what we're actually considering here. You might have to think about that just to see what I'm saying, but increasing the capacitance does increase the capacity of putting charge on. So that if I then took this capacitor, put it back in that same circuit that we used to charge in the first place, I could then put more charge on it as long as that dielectric is inside. Again, that's a different scenario than what we're considering right here, right? Okay, just having to say that because that's one thing that kind of, when I was first learning this, I don't know, somehow I missed that and it just screwed me up for a while before I figured out what was what. Anyway, and yeah, finally the energy. So how do you do the energy? Now you can go, Braun, or not so, Julia. Now you can do what you said. Now that we understand this, we have the relationship between capacitance. We can go back and use one of those equations to manipulate. We can just plug it in now. That I agree. And again, it's a scenario where we're not putting the capacitor back into the battery. We have a certain amount of charge on it. We put the dielectric in, and we want to see if the stored energy changes. Relatively speaking. So to figure out what the relationship is between the initial and final energy. So let's do that. Yeah, so we said that U, potential energy, this is not energy density now, this is. So it's 1/2, and we can use a couple of different versions. Let's use QV, Q delta V, yeah. So again, the charge is not going to change. So then we could say for Q naught, we have U naught and delta V naught. And then for the other one, U is equal to 1/2 Q V. Again, we can I mean, it's a couple ways you can do this. You can still do the energy thing. I just divide the equations. That's, for me, that's the better one. So U naught over U, the 1/2 Q goes out, so we have V naught over V, which is chi. So so U is equal to U naught chi. So the energy in the capacitor is reduced. And you should expect that, right? Because we know that the energy density is, I mean, we're saying we're decreasing the field inside here. And just from the point of view of energy density, you could have guessed that, right? Because energy density, we just define that as epsilon naught E squared, or 1/2 that anyway, right? So if we're saying that the electric field decreases in the volume, then the energy density is definitely going to increase, right? So the amount of energy then is going to decrease as well. So that's consistent with what you would expect as well. But again, listen to, be careful, be very careful about this, because this is the scenario for having taken the object out of the capacitor and manipulating it, right? So the amount of charge is set based on that. But essentially, what it does is it makes a capacitor more able to store energy. So in other words, let's put it to you like this. Let's say that whenever I had this capacitor and I put it in a circuit, essentially what we're saying is that it's going to charge to its maximum capacity, right? And it will have this voltage will be the voltage of the battery. But I take it out and then I put a dielectric in, and for the same amount of charge, the voltage now is less than the voltage V naught, which means that the dielectric now, or the capacitor with the dielectric, has a smaller voltage than the voltage of the battery for the same amount of charge. Now, these last 2 points, I've increased the capacitance and therefore increased or decreased the energy. But if I've increased the capacitance, that essentially means that I've increased the total amount of charge that could be placed on the capacitor, because I've decreased the potential. It's not it's like a different capacitor. It's not at its maximum voltage anymore. So if I now take that same capacitor with a dielectric in it and place it back into that same circuit with that same battery, I will actually be able to put more charge on the capacitor because the potential is less than that of the battery. In other words, I'll charge it back up to V naught again, but the only way I could do that with the capacitor in is put more charge on it than the Q naught that it had originally, which means that I've increased the maximum capacity of, that's what this means, really. That's a kind of a qualitative way of thinking about equation 11, is that I've increased the capacity of the capacitor to store charge and therefore store energy. So it means that I'll be able to put more charge on it than Q naught, and I'll be able to store more energy in it
then U naught without having to do anything to the capacitor. And I've done all that by simply sticking a piece of plastic between the plates. So that's why we use dielectrics, because it gives us more control over manipulating the characteristics, the important characteristics of a capacitor. Does that make sense? Questions, problems, troubles, gripes. Julia, does that make sense? I know. You have to think about it a little bit. This takes a little bit of thought. Right. Thank you, Julia. The mathematics is simple, but maybe go back and look at. I don't know if you walked away a little bit, Ron. I don't know if you were back, but maybe because I need to move on. But I said it. I think I said it well. So you might have to go back and look at this section again and think about the stuff that I'm saying. Yeah. It's not that difficult. It's just actually it's not really difficult at all. But it's just there's some subtleties there, and one of the issues, as I said at the beginning of this course, is that we have to develop an intuition to visualize what's happening, and we got all these different models and 2 or 3 different models for the same thing, just to, but you keep kind of going over it in your mind, and then you start to get some clarity and then see it. Yeah, I know, right? I didn't have recordings back in the day. All right. So that's what happens. We actually haven't talked about why, but you were on the right track. So let's talk about why a little bit before we move on. 11:04. Yeah. Might not actually get to circuits. And the why has to do with what's happening inside the dielectric. We can talk about that a little bit, and then we're done. So all of that is what happens. Let's now talk about why it happens. Physics. Oh, Lord. Oh. I just don't want to screw this up, so I'm kind of thinking through it in my head before I start talking. It's really interesting, man. Anyway, here we go. Thinking through it in my mind. Well, all of this started, this kind of cascading or domino effect of all these things changing, these quantities, and ultimately the properties of the capacitor changing, simply because of the field decreased. That was the beginning of all of this. So let's go back and take a look at why the field decreased. What caused the field decrease? So I said the dielectric is a piece of plastic. I mean, in a more general term, it could be any kind of insulator. I think probably even if you put a piece of wood in there, it could act like a dielectric. So, but I think the ones that are used, commercially, usually some sort of polymer. But it basically is just an insulator. So that's really a better statement, is that a dielectric is an insulator. So we've described an insulator in terms of, the model of a solid, right? The main difference between an insulator and conductor is a conductor has free charge and an insulator does not. So a dielectric is an insulator. Okay. Now, let's consider this polarization. We talked about polarization of an insulator. Remember when we were talking about, rubbing your sweater with the balloon and sticking it on the wall? And we went back, we talked about how the bound charge, both of those are generally insulators. The plastic is an insulator. The sheetrock of the wall is an insulator. So why does it stick? Well, you rub off excess charge from your sweater, so there's excess charge on the balloon. You take it close to the wall, but there's atoms in here, right? Remember the Einstein model, and we built on top of that. The insulator, they have bound charge, and the bound charge of the atom becomes polarized, right? Like if there's free charge on the balloon, it click close to the wall, the free bound charge on the atoms on the surface of the wall, they feel the field from the negative charge of the balloon, and they kind of shift away, and it causes each atom to be kind of polarized, so it has a small electric field. So it's that same polarization effect that we're talking about. But let's just revisit that and think about it. I'm going to revisit that in the case of one atom, and illustrate how that happens, and then show what's happening in the atoms in the dielectric. So polarization charge or bound charge within a dielectric causes the reduction of the field between the plates. Bound charge resides on the surface of the dielectric. Yes. Or polarization charge. So let's just, we'll write the reason, then we'll describe it. So polarization charge. So we all got all this charge. You got a free charge, you got bound charge, you got excess charge. Now we got polarization charge. Oh, this charge. Polarization charge or bound charge. It's kind of polarization charge is essentially bound charge behaving a certain way on the surface. on the surface of the object. So polarization charge within the dielectric reduces the field, behaves in such a way that it reduces the field between the plates. So polarization charge, balance charge within the dielectric. I'll just say behaves in such a manner that causes a reduction of the field. Between the plates. Yeah. All right. So if we take the atomic model, simple model of an atom. Wrap this up, atomic model. So, let's just take a very simple, what is this, a hydrogen atom? Yeah. A hydrogen atom. Hydrogen is one proton and one electron. Yeah, one electron. It's just simple. So, yeah. So, atoms are electrically neutral. In fact, everything is neutral in matter. So let's say that we have a so yeah, we have the atomic number. We have one proton. So this is +1. And then we have an electron that is, now it's like we kind of think of the model as an electron cloud, right? But the cloud is such that, let me just draw a circle to represent the cloud. It's around the thing. Now we know it's more complicated. That's, energy levels and all that. But we could kind of think of the cloud as the place where the electron exists. But the electron is a negative charge. So I'm just going to point to this cloud, and this represents the boundary of the cloud as negative. But what is true is that wherever that electron is in that cloud in any given time, over a period of time, the places that the electron can be is symmetric, and that's the key, symmetric about the center of that cloud. So then on average, if it's symmetric, then you could say that on average, the negative charge is in the center, right? It's like there's no separation of the negative charge and the positive charge if it's symmetrically about the center, right? The average value of the charge is in the center where the positive charge is, so that there's no inherent field associated with the atom. That's the best way that I can explain it. Yeah. And so this is what an atom looks like whenever there's no external influence or forces or anything. And in fact, that's what an external electric field is. And so when the external electric field, which I'll call E, external or just E naught, because E naught is the field that's in the dielectric or in the capacitor between the plates. And this is where we're going to place the plastic. And so like this is like a charge that's inside. This is an atom that's inside the dielectric. So when the dielectric is not in the vicinity of the E naught, the field between the plates, when E naught is 0, then the atom is like its normal self, and there's no, there's no, it's not polarized. So this is no external field and no polarization of the atom. Okay. But now let me take that atom and place it in and place where there's an external electric field, i.e. take the dielectric and put it in between the plates. Well, now there's something else that happens. It's almost like, and remember, the atom doesn't move. So it's there because, it's connected like the Hooke's law to its springs, and it can't move. We talked about that. But what can shift is the average position of the electron about its, the bound electron, the bound charge about its, in fact, let me just call this E bound. So this is the proton here. This is the proton. So I'll put symbol P there. Oh, yeah. So that's a proton P. And this is an electron, right? Let's see, yeah, and it's average. So anyway, it's in this cloud, but that cloud, in our case, if we say that the electric field, and the way I drew the picture, it was pointing from left to right. So now E naught is not 0, and it's in there, and it's pointing from the positive plate to the negative plate, right? So this cloud sees an electric field. And remember, the positive charge can't really move, so it doesn't really shift much. But the electron, it wants to go toward the positive plate of the capacitor. But it can't really just move over there because it's bound to its atom. So it shifts a little bit. So it breaks the symmetry that it had prior to being exposed to that external field. And again, this is just a model, right? So it doesn't probably look like this actually. But just if it did, maybe it looks a little bit something like this now, where the symmetry is kind of broken, right? That it's shifted over a bit, something like this. I don't know. I get in the middle. Let me draw the thing first and then just. So now the proton is shifted over a bit. So the average value of the electron is now somewhere else, right? Is like maybe this represents the negative, right? So now what you have basically is a little bound, we call it E bound. It's like a little electric field associated with the atom itself that has an opposite. Remember, electric field points from positive to negative. So now there's a little field in here that's opposite polarity of the external field, like that. So I'll call that EB for the electric field associated with the bound charge of that atom. Okay, check this out then. So remember, this is an atom inside my dielectric that's also now placed inside my capacitor. Now, let's go back to the capacitor and look at this. Here's my capacitor again. And I think I had my excess charge on the outside like this. Now, my dielectric, it's inside here now, right? I'm not going to draw it flush with the wall just because I want to clear. Now, I'm going to represent, I've got who knows how many atoms in this thing. And all of my atoms have this going on. So I'm going to draw like little things to represent my atoms like this. Kind of like my drawing is not going through. I'm trying to make ovals, but whatever. And in all of these little atoms, I've got this going on, where now my thing has shifted over, my cloud, and I've got a little EB in there. And I'm going to draw little vectors that represent all these little bound electric fields on this thing. So, and they're all pointing, oh, let me use green since I use blue for the thing. They're all pointing in the opposite direction of the E naught, pointing in that direction, little arrows. So that's EB, all the little EBs. And of course, I still have my E naught that's trying to point from left to right. I'll make that purple this time, right? So I'm trying to I got big E that's doing this, E naught. So now we can see why it's decreased, because the electric field abides by superposition, right? And basically, the total field now has got to be the combination of E naught plus the collective sum of all the E sub B's, which I'll just call E sub B, right? Like this is like E sub B I, like the I E sub B associate, but you add them all up, you're going to get a collective field in the opposite direction. I'll just put it up here someplace. I'll call that, I should put it down here in the dielectric somewhere. So that in that direction is EB. So now the net field that I actually will measure, or the field will be reduced by, so E, the total field now is going to be equal to E naught minus EB. And that basically explains why the field is reduced. Where the E naught is associated with the excess charge, I guess, on the capacitor plate. And we can also do something. We can conveniently, for the very last thing I'm going to do, I can describe this charge in terms of charge density. We generally say that the excess charge on the capacitor here, that's due to its free charge, we say, because it came from free charge. So we usually refer to that as sigma F for the free charge density, free charge. And we refer to because there's also, like on the surface here, another way you can, I did this in terms of field, but I can draw another picture here where, let me just take, like on the surface of this dielectric, there's actually charge that accumulates. Like if you looked at this picture, like if this atom were right on the surface of the dielectric, well, whereas before the external field was there, E naught was there, it was neutral. But now, because it's split, when you look at the surface of the conductor, this side here looks like it's negative, because the negative charge is kind of polarized on the surface, and it's trying to counteract some of the field, which it does, of E. It's canceling some of it. So like on this, let me draw the picture again. It's a little bit better. All right, so, over here, forgive the fact that I didn't put that charge, that's the sigma free. But now when I put my dielectric in, on the surface, due to this polarization effect, I'm going to get what looks like negative charge on the surface. It won't be as much as the sigma free, but it'll be some, enough to cancel cancel the field, to cancel a little bit of the field lines trying to go through there. And on the other side, I'm going to have sigma plus. All right, the same amount, but just plus on the capacitor, equating those because they have the plus on the other side, right? So that stuff is what I'm calling, this is called bound charge density, E sub B, because it's associated with the bound field and the bound charge inside the dielectric. So another way you could think of it is when you stick that dielectric in, bound charge appears on the surface of the dielectric and cancels some of the field lines trying to go through, which is why ultimately it diminishes and you only get a certain amount of field going through. So that's why we just discussed previously what happens, but this is why it happens. So hopefully that's kind of helping you to visualize a little bit better dielectric, Brian. And it's one last thing that we can do. Oh my gosh, it's 11:29. Well, there's an equation you can quickly derive, basically using this equation here. And yeah, I can do it really quickly. Or maybe I should get you the answer and let you do it because they should do it in the book. We actually know what the field looks like, right? We determined with Gauss's law maybe a week or so ago, that the field outside a conductor, it looks like this, right? In general, the field is sigma over epsilon. So if we have the charge density, basically the E naught or the free field is equal to sigma free over epsilon naught. This is a little bit of hand waving. Technically, you can have a different epsilon inside the dielectric, but in the ideal case, let's assume it's the same epsilon. So, or in fact, you can, yeah, we'll just leave it at that. Then E bound is equal to sigma. Actually, that's not true because we're not on the inside. Right? We can think about it on the outside. Whatever. There's a couple ways to describe, but the bound charge is sigma bound over epsilon, right? So using that relationship, and I'll let you maybe do it as an exercise. So using these two things, let's number them. It's equation 1, 2, 3, and also using the relationship that E equals E naught over chi, you can show the relationship of the sigma bound to the sigma free. You can do some algebra and manipulation and stuff, and ultimately you can show that the absolute value of sigma bound, I'm going to put it up here, that the absolute value of the bound charge density is equal to the free charge density times this quantity, or the magnitude of the free charge density, times this quantity chi minus 1 over chi. And what it shows you that you can never have as much bound charge as free charge. So this relationship shows that you will never be able to fully cancel the field by sticking a dielectric in. Because I've run out of time, I won't derive. It only takes about 3 or 4 steps. But you take these equations and you can basically plug all this stuff into here and then manipulate the algebra and you can get this equation. And it shows basically that because chi is always greater than 1, that sigma bound, the absolute value of sigma bound, is always less than the absolute value of sigma free. And that's a huge point of the limit on the dielectric. Okay, so kind of done. And some books, this is actually the end of the chapter. I think in your book, they put capacitors, circuits inside this chapter as well. So, or maybe they don't. Oh yeah, actually they do. Capacitors in series and parallel. They put. So we'll finish up because that kind of leads into, I like to do that. Some people have this as the last section of the chapter, but I like to do the circuits as the last section because it's just kind of analogous to what we're going to be doing in the next chapter or next two chapters. Okay, well, I think